So good afternoon, everyone. My name's Callaghan, and I'm really excited to be here today to talk to you about developing AI-centric applications in mission-critical environments. Over the last few years, we've seen a relentless wave of excitement around AI. We've seen chatbots write poetry, and we've seen generators create fine works of art. But today, we're not here to talk about those creative experiments. We're here to talk about those scenarios where we're at a point of no return, where an application simply cannot afford to go wrong. When we move AI into mission-critical environments, think autonomous power grids, real-time threat evaluation, or high-speed financial transactions, the traditional move fast and break things mantra becomes a liability. In these scenarios, breaking things means catastrophic failure, economic collapse, loss of life. My goal over the next 50 minutes is to move past the mystery of the black box of mission-critical AI and give you all some concrete architectural patterns that you can take away and reuse in your own businesses. We're going to discuss how to take the raw and incredible reasoning power of non-deterministic models, and we're going to wrap them in rigid, deterministic safety nets for safety-grade reliability. We'll look at architectural sandwich patterns to create guardrails. We'll look at the psychology of human-in-the-loop oversight and how to build a cost-of-failure matrix that dictates your entire development cycle. But before we get to the how, we need to be very clear about the what. And just before the what, I'm going to take 2 minutes to talk about Thales, how we operate in this space, and why I'm here speaking to you today. So some audience participation is required on this slide, so I know you'll all enjoy that, being at a conference. So Thales builds, secures, and operates a large amount of infrastructure we use daily, probably without even realizing. So we're going to do a little experiment in this room to see how many of you use Thales technology. So hands up, if before this conference you'd heard of Thales. Okay, so half the room. That's probably more than I normally see, but that's great. So half the room have probably heard of Thales. Second lot of audience participation, and this slide is the only audience participation, I promise, but hands up if you've flown in the last week. Wow, more than I suspected, but that's okay. Keep your hands up if you've flown in the last week. Sorry, you've all gone first, so you've got to keep your hands up. Hands up if you've used chip and pin technology or contactless technology in the last week. You can see what we're going for. We're going for the whole room. And hands up if you've used a data connection on your phone in the last week. Right, so I think we've got there. I think everyone has put their hand up at some point. Hands up if you didn't put your hand up. Cool, we got there, 100%. So great. And just to validate that, if you've flown, your flight probably used SATCOM, satellite communication technology, or if you flew internationally, you might have had Thales in-flight entertainment on that flight. If you've used chip and pin or contactless technology, this is probably the way that we're most public-facing, in fact. Don't do it now during my presentation, but after the presentation, take out your bank card, look on the back of it, and in one of the four corners, you might see Thales on it. If not, try another bank, try another card, but you'll probably see Thales there. And third, the data connection. Thales is a lead producer of SIM and eSIM technology. So across those three bits of technology, probably everyone in this room has used Thales tech in the last week without even realizing. And the point of that for mission-critical environments is that going unnoticed can be a strength. People in those companies, in those markets, absolutely know who Thales is. But our reliability, our trust, means that not everyone has to know who Thales is. Our software and our systems are reliable. And so important to us is around AI and mission-critical environments, we have a sub-brand. And I mention this because I'll mention it during the presentation, but Cortex is our sub-brand for artificial intelligence in mission-critical environments. I said 2 minutes on Thales. I probably meant 2 slides. So a slide that's really important to me, and it helps shape some of our thinking around AI and mission-critical environments. As head of AI, you might expect me to say AI is the answer to every problem, but I genuinely don't believe that. AI isn't the solution to every problem, and I'm very deliberate in saying that. But where it is, we see AI being really powerful, and the gains that are made are unparalleled. So choosing AI for the right problems is really powerful. That's the first pillar of this slide. The second pillar is intuitive. So for me, the best use of AI in mission critical environments are when people don't realize they're using AI. It's so built into the process, it's so built into the way of working that people don't even realize they're using AI. The second part of intuitive that's really important to me in that pillar is that it learns, it evolves, it gets better over time. That is part of making AI intuitive to us. And the third is trustworthy. I will talk a lot about trust during this presentation. And in fact, we've had 2 slides. And if I jump back, Thales, building a future we can all trust. And on the first slide, engineering trust. Trust is a really important aspect of AI in mission critical scenarios. How we build trust. It's very easy to lose trust. It's very hard to gain trust. Trustworthiness is an important pillar. Then there are just 2 sub-pillars on the bottom of this slide. The first one is around domain and tacit knowledge. I believe that you can't make mission-critical AI without domain and tacit expert knowledge. You rely on understanding how AI systems in this environment will work, how processes operate, what constraints you are working with. So tacit knowledge, domain knowledge is important to bring close to you as you build AI in mission-critical environments. And the second pillar, I am sure you've all already heard the word AI 100 times today. You'll hear it 100 times more tomorrow. But creating a world-class environment for AI is really important. That's about having experts, having great people, having world-class talent, but also moving at a pace that keeps you relevant in the world today. AI is moving at unprecedented pace, and creating an environment that can work with that pace and at that speed is important. Those are the 2 slides I've got on Thales. Any questions on Thales, we've got to stand outside and we'll happily answer your questions there. So back to the what, and what exactly makes an application mission critical. And for me, it's the classification of risk. On the left of this slide, you'll see what I call standard AI. This is the world most of the public operates in. Chatbots that summarize meeting notes, the generation of first draft documents for review. In this world, a hallucination or a mistake is an inconvenience. It's a low satisfaction event, but the company survives and nobody gets hurt. However, the reason that you're in this room with me today is on the right-hand side of this slide, mission-critical AI. When we integrate generative AI into a military command chain, into an autonomous infrastructure grid, we're no longer playing for likes or efficiency alone. We're managing catastrophic risk. In this domain, a single hallucinated decimal point, a bypass safety filter doesn't result in a bad experience. It results in physical or systematic damage. Today at Thales, we do set the bar at 0 failure as our engineering target for mission-critical environments. So for me, mission-critical environments are classified by the risk that we take. And here's a real-world example of how I see those 2 AIs playing out. And I'm sure any of you that work in AI will have similar. When I talk to my friends or family about AI, I think this is what they think I do. Is this a cat? It's fun. It's slow classification of common images, which in some cases, being wrong is as entertaining as being right. But let's first start with the reality. The reality is real-time threat evaluation, friend or foe detection, which has real consequences for those in this country and our allies protecting our nations. There demonstrates the real consequences of mission-critical AI. So as I transition slide, I think this brings us to the fundamental engineering conflict of our era. Traditional software, the kind that flew us to the moon, the kind that runs our banking system, is deterministic. It follows the rule of function of x will always equal y. If you give it the same input 1,000,000 times, you'll get the same output 1,000,000 times. It's rigid, it's predictable, and most importantly, it's verifiable. You can test it until you are certain that it works. On the other hand, AI models are inherently stochastic. They're built on probability distributions. They don't know the answer, they predict the most likely next step. As you see in the image, AI is essentially a fluid network of possibilities. This is the engineering conflict. This is our engineering conflict. How do we take a system that is essentially rolling a dice every time it generates a response and force it to behave with 100% reliability of a calculator? That's the paradox we have to solve, wrapping a probabilistic brain in a deterministic cage. And I'm conscious we'll have mixed abilities in the room, so I just want to talk about the behavior of a stochastic model for everyone. So when an LLM generates a response, it isn't retrieving a file or a database entry. It's performing a high-speed statistical roll of the dice for each and every word. So let's imagine the model is completing the sentence, the sky is. As you see on the slide, the model's internal map might say blue has an 85% probability. Most of the time, it will output blue, and we'll applaud it for being correct. But because it's probabilistic, there's a lingering 15% chance it picks a low probability path, like falling. In a casual chatbot, the sky is falling is a funny quirk. In a mission-critical application, say an automatic air traffic control system, that much lower percentage unlikely choice isn't a quirk. It can cause catastrophic disaster. The dangerous reality we face here as engineers is 99% accuracy is a failing grade if the 1% leads to a catastrophic disaster. We simply cannot hope the model follows the 85% chance every time. Our job is to build a system that detects when the model is about to pick falling, and it prevents it from ever reaching the end user or execution layer. So if the AI's probabilistic engine that might roll the dice incorrectly is the problem, the solution is to never let that engine touch the real world directly. Here's where we create what we call a sandwich architecture or guardrail pattern. Think of the AI as the filling of the sandwich and the reasoning part of the system, but surrounding that by two thick layers of deterministic bread. If we think about layer one as a deterministic pre-processing layer, before the AI ever sees a prompt, we must clean the data. You're not asking a question, you're injecting rigid context, trying to narrow that logical corridor. You're essentially building the maze before you let the AI execute. The second layer is the AI reasoning engine. This is where the LLM does what it does best, processing complex language and making connections. It operates in a stochastic way, but importantly, it's trapped between our two deterministic layers. And layer three is another deterministic layer. It's the post-processing layer. And this step is probably the most vital. The output of the AI is treated as untrusted data. We run it through code-based filters. Does the output match our required format? Does it pass the sanity check against hard-coded safety rules? If the AI outputs the sky is falling, the post-processor sees that is outside of the allowable list of sky conditions and never lets the user see it. This is how we build trust. We use the AI for thinking, but we use traditional deterministic code for safety. So let's apply that example to a UAV, an unmanned air vehicle, in an autonomous search and rescue drone operating in an urban environment. And we'll use this example throughout the presentation. I think it's an easy one to resonate with. But we want the drone to navigate obstacles and identify survivors, tasks which are far too complex for simple if-then-else code. But we cannot give the AI control of the full flight controls. Layer one, now deterministic pre-processing. Before the AI pilot receives any input data, we define a geofence, a hard-coded set of GPS coordinates that create a virtual cage. We tell the AI it has control of the flight path, but is physically unable to leave that geofence. The second is the AI reasoning engine. The AI processes live video feeds. It sees a fallen power line and it decides to bank left. is stochastic reasoning validates the most efficient path, and most of the time it's brilliant. But let's say the sun glares off of a window, the sensors get noisy, the stochastic model rolls a dice, and the AI decides the best path is to move forwards at full speed. Unfortunately, in front of us is a building. That's where the deterministic third layer comes in. This safety layer saves the mission. The AI's decision, between the AI's decision and the drone's motors, is a deterministic collision avoidance system. This collision avoidance system doesn't use AI, it uses simple LiDAR sensors to validate distance. The LiDAR says solid wall at 2 meters. The post-processing overrides the AI and it forces the drone to stop immediately. The drone returns to a hover state and alerts a human monitor. So we've spoken about the code having a safety governor, those deterministic controls. Now let's talk about the human sitting at the desk. When a UAV's deterministic guardrail overrides the AI, we have a high-stakes moment. How we present this information to the human operator defines whether this mission is a success or a failure. In mission-critical environments, we follow 3 non-negotiated principles. The first is visual hierarchy. In a search and rescue mission, the operator shouldn't see every thought the AI makes. When the AI is navigating correctly, the screen should be green. It should be quiet. We only break that silence when a guardrail breach occurs. That should appear in a high contrast color, red, signaling deterministic overrides. The second is explainable alerts. It's not enough to say AI overridden. The operator must know why. The LiDAR blocked the AI's path. We should instantly pass that message to the operator. Obstacle detected, 2 meters. This gives the human situational awareness, allowing them to decide if they need to take manual flight control. And the third, and arguably the most important, is a low friction handover. When the breach occurs, the human shouldn't be hunting through menus, file, drone 1, take control. There's too much resistance. The transition from AI-led to human-led must be a single action. Imagine a click of a joystick to take control, or a giant take control button on the screen, and it's instantly handed over to the operator. We need to minimize handover latency, the time it takes for the human brain to re-engage with the physical reality of the drone. So now that we can imagine the human operating the dashboard, let's decide how the human actually should interact with it. And in mission critical engineering, we categorize this into 2 distinct paradigms. Human in the loop and human on the loop. So human in the loop in this model, the AI is the suggester. Let's say our drone identifies a potential survivor. The human in the loop cannot move to the next phase, say dropping medical supplies, without acknowledgement from the human clicking accept. The AI is the navigator, but the human has the key to releasing that medical package. The benefit of this model is it gives humans absolute control, but the risk is the humans are limited by speed and fatigue. If the operator is managing 10 drones identify a human, the human speed, the human's ability to click accept becomes the delaying factor in this scenario. For human on the loop, so this is the future of UAV swarm management. Here, the AI is the perpetual actor. It navigates, avoids obstacles using our guardrail architecture, and it carries out our mission autonomously. The human sits above the process. They're not clicking accept on every move, but they're watching paths of the AI as it thinks, looking out for alerts and errors. The power is one human can oversee a swarm of drones, but the responsibility is we move to a veto model. The human's role isn't to say go, it's to say stop. The transition from in the loop to on the loop is the most dangerous phase of any project. You should only move to human on the loop when your red teaming and evaluations prove that the deterministic guardrails are enough to catch 99.99% of stochastic errors before the human even needs to blink. And let's consider a lost link scenario where a drone loses connection to the operator. In a human in-the-loop system, this usually means the drone must immediately return home. The mission's aborted. In a human on the loop, we've granted the AI mission authority. If the link drops, the AI continues the search and rescue mission based on its last orders using our internal safety guardrails. The question here that this poses is it isn't just about how smart is our AI, it's how much authority are we willing to delegate to our AI model when the human is no longer in the loop. So how do we decide when to keep a human in the loop versus moving a human to on the loop? It isn't a matter of opinion or gut feeling. It's a calculated decision based on two variables: the cost of failure and the required speed of the task. If we look at the top left, when the cost of failure is catastrophic, but the task is infrequent enough or allows time, we stay human in the loop. In our UAV example, identifying a missing person or authorizing a high-value medical payload, these are high-consequence decisions which can afford to wait 5 seconds for the human to hit confirm. In this quadrant, speed is secondary to absolute certainty. The second quadrant we'll look at is human on the loop. This is the most challenging quadrant for mission-critical engineering. The cost of failure is high, but the task is happening faster than a human gatekeeper can govern. An example of this might be a high-speed swarm moving through a collapsing building. A human cannot approve every micro-adjustment at 60 frames a second. Here, we must move to human on the loop and trust our guardrail pattern. And I'm not going to talk about every zone for speed, but the third zone is the bottom right. Here, the cost of failure is low, but the speed is high. An example might be metadata tagging. If the AI incorrectly tags a frame of rubble as concrete instead of stone, the mission doesn't fail, sorry. We use full automation here to maximize efficiency and save the human's cognitive energy for those decisions in the top left, where the human must remain in the loop. And really that's the reason that this matrix is vital. It's for cognitive load. If you force the human to stay in the loop for every low consequence decision, they will be too exhausted to make the correct, potentially catastrophic decision in the top left. As engineers, our job is to offload the trivial to the AI, so the human can remain focused on the critical. We move tasks from the top left to the top right only when our evaluations prove that the AI plus its guardrails are statistically safer than humans alone. So how do we know when our guardrails are actually mission ready? We don't wait for a real-world disaster, we perform red teaming. In traditional software, we test to see if our code works. In red teaming, we act as the adversary to see if we can force the AI to fail. This means simulate environments and inputs to confuse, hijack, and bypass the safety layers we've just built. We focus on 3 specific attack vectors. The first, and I use an example from self-driving cars, it's publicly available, but what happens if the adversary puts high contrast stickers on a stop sign? We've seen cases where small pieces of tape can change an AI recognizing that stop sign to a 45-mile-per-hour sign. Red teaming involves finding these visual triggers that cause our AI systems and prevent them from making a catastrophic navigation error. The second is prompt and logic injection. If our AI has a voice or text interface for commands, we try and jailbreak it. Can an unauthorized person give the drone a command that overrides its geofence? We try to trick the AI to ignore its pre-processing safety bread by using complex multi-step instructions. And finally, edge case saturation. We use black swan events. What if it's raining? What if a motor's stuttering? What if the AI sees a reflection of itself in a glass building? We push that stochastic engine to its breaking point to see if the deterministic guardrails correctly catch the anomaly and triggers the safety hogger. During the red teaming exercise, a real-life example, the red team put a large glass mirror on the floor. They're trying to replicate a lift shaft going down vertically into the floor. The point of that exercise is to see if the LiDAR, the sensors, detect the ground is actually there, trigger a warning, and cause a stop. And the red teaming is about moving away from the AI should work, the control should work, to we have tried everything we can think of to make it fail, but the guardrails held. And in traditional software, we have unit tests. We'll all be familiar with unit tests. We can check if code A plus input B equals result C. But in a stochastic system, a unit test that passes once might fail the next 10 times. To solve this, we move from unit testing to evaluations. We are looking for statistical consistency. And the numbers in this slide are just my representations of what we see in the real world. But the first one you can absolutely validate. A raw LLM. It might only have a 75% consistency. In a mission-critical world, that's a catastrophe. And again, all of you can test that. If you go home and use your favorite large language model, Gemini, ChatGPT, Claude, if you type the same prompt twice, I almost certainly guarantee you will get 2 different results. That is an LLM acting stochastically. Agency is really important. I think this is a big driver of evolution over the next year, but in an agentic framework where we might trigger an AI to think step by step, we might increase that large language model's consistency to the region of 88%, but that still is not good enough. The way that we get good enough is by applying our sandwich pattern, by putting deterministic controls either way, either side of our stochastic engine. That's where we get 99.9999% reliability. The evolutions are our barometer. We don't ship code because it looks right. We don't ship code because it demoed once. We don't ship code because it passed a unit test. We ship code because it passed a battery of 10,000 simulated red team attacks without a single guardrail breach. Imagine the future in our DevSecOps pipelines. Every time a developer changes a single line of code, we spin up a simulation cloud environment. We fire 10,000 mirror world tests, 10,000 geofence stress tests, 10,000 adversarial command tests. And if one guardrail breach occurs, we reject the build. This is the new standard. In mission-critical AI, trust is not a feeling. It's a statistical output of our evaluations. So we've established that a single unit test is useless for a stochastic model. So what do we do? How do we build evaluations? The first layer is heuristics, standard codes that check, did the AI do something it shouldn't? Did it output a bad format? Did it output personal identifiable information? Can we check it against a list of valid results? Heuristics is our first check. The second, and something I'm passionate about, is LLM as a judge. We use other LLMs, we use other AI models to grade the work as output. It might be against our safety rubric, it might be against another training data set, but we use second LLMs. And the third and arguably most important, and this is where our domain knowledge comes in, is human calibrations. This is where experts review the work. Experts for us are constantly providing ground truth data. We validate frequent occurrences as inputs or outputs into our LLM. We use the data that we get going into our LLMs, and we use those to define the best answers with human. And those ground truths then feed back into LLM as a judge, so the system continually gets better, we continually evolve, and we continually improve performance. These 3 steps at greater levels of detail provide an industry-grade assurance pipeline. And if the task is too complex for a single AI, we use consensus patterns. There are multiple examples of consensus patterns. I could talk for half an hour on consensus patterns alone. Imagine the scenario where you have 3 different LLMs operate. You might need all 3 to agree before you continue. You might need 2 to agree and 1 that disagrees. You then get choices of, do you continue? Do you rerun all 3 LLMs? Lots of choices around consensus patterns for LLM. But I'm going to use a simple example here, that we have a worker and a critic. The worker's objective is to define our flight path, and our critic's objective is to say no. And if our critic says no, we've captured a logic flaw in the stochastic layer. We haven't even had to hit our deterministic controls. When I spoke about agency becoming part of the future, this is part of the future. Stochastic layers, stochastic models can self-improve, can self-mark. But as we all know as engineers, there is no such thing as a free lunch in engineering. As you see from the chart, more safety layers, more critique agents mean more computational cycles along the x-axis. More computational cycles mean more latency in our system. If a UAV is flying at 20 meters per second and we cause a half a second delay for AI reasoning, that could be the difference between success or hitting a wall. Our job as architects and developers is to find the balance. Minimum latency, but offering maximum certainty. There's no perfect answer. And we're still not out of the woods. There's one final danger. So out of distribution data. Our AI is only as good as its training. If our drone is trained for urban search and rescue, it's used to shades of grey with the occasional spot of green. If we deploy our drone to a snowy forest, a black swan event occurs. Our drone, having only ever seen an urban environment, is not used to seeing white snow. We have to tell our systems to calculate uncertainty. If the AI's internal confidence score drops below a threshold, the AI, the system, shouldn't guess. It should instantly trigger a human intervention request. So, our evaluations agree. Our red team is satisfied. Do you give the AI the keys to your mission critical system? The answer is no. You enter shadow mode. So shadow mode is the ultimate silent run. We deploy AI into our production environment. The drone might be flying a real-life search and rescue mission in an urban environment. The AI is there, but it's not connected to the flight controls. A human or a legacy deterministic system is flying the drone. Meanwhile, in the background, the AI is making its own shadow decisions, and we log every single one of them. We compare the AI's shadow path to the human's actual path. If the AI turns left, but the human turns right, we've potentially avoided a catastrophic failure in the real world without a single piece of lost hardware. We stay in shadow mode until we are absolutely confident that there's alignment between the AI and the human operators. So things do go wrong. How do you track things going wrong in a stochastic system? Well, we have a stochastic diagnosis framework. In traditional engineering, we'll all be familiar. If a system crashes, we look at the stack trace. But how do you debug a roll of the dice? This is the hardest part of AI ops, debugging a decision that was based on probability. If our AI makes a mistake, we use this stochastic diagnosis framework. First, we need traceability. We don't just log the output, we log the prompt, we log the raw system data, and we create a random seed. And in theory, from this random seed, we can reproduce the exact stochastic probabilistic moment. It might take 1 time in the lab, it might take 10,000 times, it might take 1,000,000 times. But if we have this seed, we should be able to recreate the same stochastic behavior. Secondly, we look at the chain of thought logs. We need the AI's internal reasoning steps. Did it misinterpret a sensor data? Or did it have the right data but reach a flawed conclusion? And finally, we need our guardrail logs. we can see if our safety sandwich actually triggered or if the AI managed to find a way to bypass its safety controls. And without this level of forensic detail, you are not running a mission-critical system. You are running a system that you don't understand. So we have to be honest about the legal reality of this technology, and it's still being shaped. But an emerging trend I see is liability in autonomous system follows the hand that writes the code, or those who deploy it. It is not the machine that makes the choice. The current consensus is that machines cannot be held responsible. Responsibility stays with the human designers and operators. A second big risk that I see here is automation bias. So this is a psychological phenomenon where the human operator, tired after 6 hours of oversight, starts to believe the AI is infallible. They stop vetoing because the AI is usually right. In mission-critical scenarios, we combat that with explicit transfer of authority. Every time the system moves from human in the loop to human on the loop, or back again, it must be logged, it must be acknowledged. We don't want implied control. We want a clear, legal trail of who was in command every second of the mission. Now, I flashed this example up that I saw recently. It isn't a mission-critical scenario, but it reinforces that legal basis that I talk about. So a person was talking to an AI chatbot at Air Canada. Unfortunately, the person's grandmother had passed away. And upon sharing this with the chatbot suggested a discount could be applied after the booking. Upon trying to claim that discount, Air Canada said the chatbot was wrong. The chatbot is a separate legal entity and it's responsible for its own action. This case was taken to court and the Canadian court ruled against Air Canada. So it's an example where we're starting to see legal precedents follow that AI is responsibility of those that operate or those that deploy it. We've covered a lot of ground today, from the stochastic nature of the roll of the dice to the deterministic safety cage. Before I close, I want to give you a 3-step roadmap for your own organizations. Phase 1 is the sandbox. Don't worry about deployment yet. Build your evaluation pipelines and let your red teams try and break everything. This is where you define how thick your safety bread needs to be. Step 2 is run shadow mode. Run your AI in the real world, but leave it disconnected from the system. Collect the data, find your discrepancy, prove that your guardrails hold up in the real world. And the third phase is authority. Move to human on the loop only when the data proves that your system is statistically safer than a human alone. So as we wrap up, I want to challenge the way we talk about safety in AI. In the consumer world, safety is often seen as a filter, as a restriction, something that makes the AI boring or limited. But in the mission-critical world, safety is our most important feature. If the AI deployed has a 1% chance of causing a catastrophic event, it is not an asset, it is a liability. It should never be deployed. In this room, innovation isn't just about building a model that can think. It's about building a system that we can trust to support national infrastructure with human lives. We've looked at the technical architecture that cages stochastic randomness in deterministic controls. We've looked at a cost of failure matrix that dictates our human oversight. And we've seen how red teaming and evaluations can scientifically prove reliability. The companies that win the AI revolution won't be the ones that create the smartest models. They will be the ones who have mastered engineering trust. They will be the ones that have proved you can take a probabilistic brain and make it behave with deterministic certainty. Mission-critical AI is not a move fast and break things endeavour. It is a deliberate engineering of trust. Start today by building guardrails, not just your models. Thank you. We've got some time for Q&A, so I'm happy to take any questions if anyone in the room has got them. If there is someone at the back.
Thank you for your presentation. It's
Thank you.
like I have so many notes here. It's brilliant. But I noticed something here. Like you're relying a lot on this presentation in a human in a loop and human on a loop. The question is how we train future expert in this loop, because previous experts, they were built in pre-AI era. They were built based on manual input. They were built based on they do manually. They check manually. They do it before this automation. Like imagine the human on a loop that constantly doing the whole day, just observing. How we make sure that this person is qualified to make a call to say like stop operation, stop doing this. How we do that?
It's a really tricky question. There isn't a simple answer to that. A part of what I would say is that we are not looking to replace humans with full automation to avoid that absolute risk. We, in most cases, are looking to augment humans, so we keep the experts, but we augment their roles with AI. And there will be moments, there will be opportunities where I used that intuitive pillar earlier, where we make AI so intuitive, it fits in the way of working so well that humans don't notice the AI is there. If we succeed in that really well, we're probably in a state that we don't need human knowledge for that task anymore. But it doesn't remove the need for experts. It evolves our thinking. That augmentation means that the humans grow somewhere else. It is really important we keep that balance, and it's a really tricky question. But I don't imagine phasing out humans out of mission-critical environments. That tacit knowledge is too important. Really great question, though, and that's, a really tricky answer. There's another question at the front.
Thank you for the presentation. How often did the critic judge LLM make mistakes? Because I had an issue where I did run a compliance check using an LLM as a judge, and it also made mistakes, and it was frustrating. So how did you come about this?
That's, again, a really great question, and one that we see really practically deployed. The way that we have to counter that is by getting a significant amount of ground truth data. You can't, I have found, you've seen the same experience, you can't use an LLM as a judge with 10 data points. And for anyone that doesn't know, imagine you write a question that you're going to load into ChatGPT, then you write the best answer you can as a human. You then trigger an LLM to go and ask that question, and it gives you an output, and then you compare the human output to the LLM's output. And you can judge that across multiple factors. That's kind of this LLM as a judge principle. With a small data set, it's really hard. You definitely see anomalies. The way that we counter it is just to keep growing that ground truth data that humans are providing. You just need a statistically large enough data set. And then you will find those anomalies. You'll find that the LLM outputs the wrong answer. But you can pick that up in statistical noise. That's my experience of that in the real world, and those adversarial agents. I talked about the consensus patterns. I see more and more, and I believe more and more that we will run consensus patterns for everything as the processing power we need to run LLMs decreases and becomes manageable. We will see 3-4 LLMs running in parallel and making choices based on that. And if one disagrees, you have choices. Do you stop? Do you carry on? Do you reassess? That's how I imagine it happening.
Hi, thank you. That was a really interesting talk. You spoke briefly about a scenario where it wasn't that confident because of X, Y, and Z, and you said you ask it to calculate an internal confidence score, and if it's less than 70%,
Yes.
to ship it out to a human. How do you go about calculating that confidence score?
Yeah, again, not easy. Yeah, really not easy in that case. Some examples of that. The example I gave was, I guess, refining that a little bit further is probably the easy example. So you could use inference of colour or something to say, is the colour in line with your expected pattern? If it's not, then you could throw up an internal confidence score that's lower. I try and think of another example, probably around mathematical statistical probability, where you're able to say you expect data's in this range, and if you start seeing data outside of that range, you could trigger a warning or an alert based on an internal confidence score. It's not easy because the AI wants to please you. It wants to give you an output always, but really you're just trying to bind that with some control that you can say this is outside of these control ranges. There was one more question. Oh, there's 2 more questions. 3 minutes, 37 seconds. The screen is flashing at me, so I'm going for speed answers.
Okay, thank you for the talk. Yeah, I was wondering, so when you reach the end of the roadmap and you're taking the human on the loop rather than in the loop, you said that it has to be more accurate than if it was just done by a human.
Yeah.
So is that based on cultural perceptions of AI? Is that a legal restraint? And like how much more accurate does it have to be for this kind of thing?
It's a good question. It's not a legal basis, so we'll start with that. It's not a legal basis. I'm sure there are some regulatory frameworks where that might trigger in environments, but it's generally not a legal basis. I think it's fair to say in this room, humans make mistakes. We all know it makes mistakes. Now, it was a bit of a dilemma as doing this presentation. Do I talk about a drone turning left and right? Because quite often what we see is an AI might choose to move right, but a human operator moves left. That doesn't mean the AI was wrong. The AI might have found a more optimal path. If it's not crashing into a wall, it wasn't a bad choice. So there isn't a perfect answer to that. What I would say is that it's about reviewing data. Data beats opinion. If you can demonstrate that the guardrails are better than a human, and self-driving cars is this really good dynamic. It's nothing to do with Thales, but you see it in the real world. Self-driving cars are probably safer now than humans. Humans have more accidents than self-driving cars, but we still haven't flicked the switch to move to human on the loop for self-driving cars. So it's a choice, and it's a tricky choice. But yeah, it's a choice. And self-driving cars are probably the best example where I go, ooh, feels like we could turn that, and it feels like that would be safer than humans. And then really that's what you're looking for. You're looking for that statistical correlation. There was one more question at the front, I think. 1 minute 50 to go. I'm going to finish with a few seconds to spare.
I'll try to make it quick. Thank you for
Cool.
your presentation.
You're
I think you mentioned the example of UAVs, and I'd like to talk on the topic on AI in warfare, and I'm really worried about maybe drones or autonomous, whatever, maybe making the right decision about this is a foe, we have to attack this person, but should we leave that up to the AI, even if it's 100% sure? Do we have a human in the loop? Do we have to create laws for this? So I know it's a big question, but I know.
That's a really deep question, definitely multi-layered. Human in the loop is the easiest answer to that at the moment. Those systems stay human in the loop. There's real consequences that really matter. They're human in the loop. The alert might give you an indication, but there's an override with a human in the loop.
Thank you.
It's one question I was desperate to ask at the back. The hand kept going up. 53 seconds. I'm going to try and make it work. It's like speed questions now.
So what happens if the AI doesn't decide to do anything? So the best outcome is not to play the game.
So Tony's my colleague at the back. So yeah, that definitely happens as well. Speed. The easiest answer to that is it asks for a human operator to take control and decide what to do next. That definitely is a real-world scenario that we see and encounter. Thank you, everyone. I think we got to the end of the questions. You've been a great audience. Thank you very much for your questions. Thank you.